So I want to introduce you to Jane. Jane is a principal engineer at Plant-Based Pizza, the world's #1 plant-based pizza restaurant. And Jane has a simple task. She's working on a new microservice inside Plant-Based Pizza, and she needs to ship it to production. She builds it, it works on her machine, and then, well, how hard could it be to get it in front of her users, right? And then she starts to consider the different options she has. Does she go all the way back to the 90s and run this on a physical server in a basement somewhere? Probably not in 2026. Does she run a virtual machine in the cloud? Does she use Kubernetes, or does she use serverless technologies? And some of you can probably relate to some of these decisions. You've maybe had to make them in your career. You've maybe had them imposed on you by a team outside of your control. And making these decisions can seem a little bit complicated at times. There's a lot you need to think about when you're building modern software. And I think one of the biggest myths, actually, of this AI-powered age that we're currently living through is that writing the code is the hard part. Yes, an LLM can spit out 2 million lines of code a minute, and it will probably increase your bills 10 times, but can that agent debug things in production? Possibly. Is that agent going to be getting paged at 3 a.m. when something breaks? No, of course not. That is you. You are the one who is going to get paged. You are the one who is responsible for the code that hits production. The user load increases 10 times. Well, that's your responsibility as well. And most importantly, can the system evolve over time? Can it deal with changing requirements? Guess what? That's all of your responsibilities as well. This talk is about managing those things, managing getting applications into production, the things you need to think about as you do that over time, and how you understand your applications once they are actually running in production. I'm James Eastham. I'm a developer advocate at Datadog. Before that, I worked at AWS for quite a few years. I've been a developer. I've always developed software most of my career. I'm a Microsoft MVP. I'm an AWS community builder. But enough about me. You're not here to care about what I've been doing. The fundamental challenge that Jane is dealing with when she's trying to ship this software, when you peel back all the different layers, you peel back all the different problems that she needs to deal with, primarily she's dealing with change. One of the only constants that exist in software development. Changing business requirements, changing user profiles, changing user loads, user volumes, a change in focus from the business to be more sustainable, to be more cost-effective. Heck, even a mandate from a government somewhere in the world that restricts your access to a SaaS product. Change is absolutely inevitable in software. And here Jane needs to change the system in some way. She's building a new service which is causing a change to happen. And when it comes to building and shipping applications to production, I think the #1 thing all of you need to be thinking about is evolvability, the most important architectural ability. With software moving as fast as it is today, you need to be able to react to that change. And this importance of evolvability was even codified all the way back in the 60s by a guy called Ross Ashby. He's a cyberneticist and a psychologist with Ashby's law of requisite variety, which states when the variety or complexity of the environment exceeds the capacity of a system, the environment will ultimately destroy the system. So basically, if the system can't respond to the environment around it, the environment will always win. You can see this playing out in the real world outside. As the environment, the world, the climate changes, individual ecosystems can't deal with that change fast enough. The environment will always win. Always. And you can apply this same idea to software as well. I've recently read this book, The Architect's Paradox, by a guy called Barry O'Reilly. Has anyone come across any of Barry O'Reilly's work? Couple of hands. Even if you don't consider yourself a developer or an architect, I would highly recommend checking out this book. It's a brilliant book. And one of the key takeaways, at least I took from this book, is that software operates in a really interesting place when you compare it to more traditional forms of engineering. So if you were going to engineer a building, and I'm not an engineer, so I'm probably massively oversimplifying this, but if I was to go and engineer a building, there's a reasonably fixed set of constraints that I'm dealing with, right? The laws of physics, pretty static at this point. Gravity doesn't change all that often, at least as far as I'm aware. So you're dealing with a fixed set of constraints around the thing that you're trying to build. But software isn't like that. Yes, the thing that we build, the thing in the middle, might be deterministic, at least it was historically, maybe not so much now. But the environment that that deterministic thing operates within is anything but fixed. You've got a massively changeable set of constraints. Constraints that sometimes you don't even control, you can't even plan for. So you need to optimize for evolvability, evolving your system over time, which is much easier said than done when you're dealing with all these different decisions that you need to make. So before we come on to some of the practical things that we need to think about, I think it's really important to be really clear on the language that we use day to day. So just to define a couple of terms. One term I've used a few times already is complexity. So what exactly is complexity? It's really important to be clear on the words that we use and the meaning we're trying to convey. So if we take the Cambridge English Dictionary definition of complexity, it's something that is difficult to understand or find an answer to because it has many different parts. Now, this could mean a couple of different things. It could be that the system you're working on, the problem you're trying to solve, just has a lot of different dimensions to it. Therefore, the thing you need to build needs to have lots of different parts. Equally, it could be a function of really bad design. So whilst on this subject, I also like to define another word that's sometimes used interchangeably. And historically, I've used this interchangeably as well. The word complicated. Is something complicated? Is something complex? And there's a really important distinction between the two. So the definition of complicated is something that involves a lot of different parts in a way that is difficult to understand. Very similar, but there's a subtle difference there, subtle distinction. And I think it's a difference of necessity. Complexity may be necessary because of the nature of the thing that you're building, what would be known as essential complexity. Complexity that's inherent to the problem domain you're trying to solve. And whether you're building user-facing software, whether you're on a platform engineering team, there is going to be an inherent amount of complexity to the thing that you're trying to solve. You'll all have it, you'll all be aware of it, it's probably what causes you the most headache in your day-to-day work. But there's another type of complexity where we start to stray into the complicated. It's accidental complexity. And a lot of the painful stuff we find ourselves doing day to day sits in this category. Remember, the definition of complicated was something that involves a lot of different parts in a way that is difficult to understand. Anybody here using Kubernetes? Anyone here deploying thousands of Lambda functions to 10 different AWS accounts? No, that's just me. OK, cool. Yeah, I did figure that would be the case. And it's important to remember, of course, that these things aren't always technical. The software we build has humans involved, and you'll often hear the term that software systems are socio-technical systems. The technology is really important, and it can be complicated, it's probably complex, but so are the humans that build the software. Remember, the definition of complicated involves a lot of different parts in a way that is difficult to understand. I don't know how many humans you've ever dealt with that are difficult to understand, but I've certainly dealt with a few. So your current system might be low complexity from a technical perspective. Maybe it's a single server, single process monolith running on a server somewhere. But as your social complexity starts to grow, you get more and more developers contributing to this same system, to this same code base. That is its own type of accidental complexity. You're starting to stray into the complicated. And if you're starting to shift to building microservices, to building more distributed systems, these aren't a solution to a technical problem. It's a solution to a social problem, breaking these things down so you've got smaller teams of people, smaller groups of parts, contributing to a code base. Because, of course, microservices can feel a little bit something like this sometimes. If you've got that distributed set of hundreds of services deployed on tens of Kubernetes clusters, or you've got thousands of Lambda functions, it can feel a little bit like this. You've got inter-service communication, resilience, observability, cascading failures, cluster management, cluster upgrades, AWS deciding to blow up a data center or a runtime being depreciated. There's all these things that you then need to think about. So where do you even begin when you're Jane, who just needs to ship this application into production? And this is where, in my opinion at least, the word serverless gets really powerful. I saw some of you visibly recoiling a little bit when I put that on the screen then, sorry. And the word serverless has been co-opted by marketing teams, by service teams, by people getting angry on the internet about what serverless is and what serverless isn't and how much pain it's going to cause you. For me, the definition of serverless is different, and it's not what you'll read on the internet. It is simply about reducing unnecessary complexity. Because your users don't care how well you can upgrade a Kubernetes cluster. Your users don't care about how quickly you can upgrade a Lambda runtime. Your users care about the thing that you're building solving the problem that they need it to solve. And that's it. They don't care about any of that other stuff. So serverless as this idea of reducing unnecessary complexity. It's also useful to try and get out of this natural recoil that you might have to building with serverless, to think about serverless as a spectrum, not as a binary decision. A spectrum that looks a little bit something like this. And I'm just going to spin around for a second because I always get my left and rights wrong here. So on the far right, you've got the lowest amount of operational overhead. This is being as serverless as possible, if you will, where everything below your application code becomes the cloud provider's responsibility. All you need to care about is writing code, shipping that code, solving the user's problem. The trade-off there is these services are typically very opinionated. They force you into a certain way of building. You lose flexibility in your infrastructure. And the other end of the spectrum, of course, is running a server under your desk in the office. There you've got the most amount of infrastructure flexibility, the trade-off being you take on an awful lot of operational overhead. And there's no right or wrong place to be on this spectrum. And there's also another really important dimension to this spectrum, the cost dimension. Often when you read about serverless technologies, one of the common sticks it's hit with is that it's really expensive. It's going to cost you loads of money. Which is true. If you could compare a serverless function to a virtual machine, yes, the line item cost you get from your cloud provider is going to be higher because you're paying the cloud provider for the privilege to do all that stuff that you don't want to care about and your users don't want to care about. But this often misses the human cost. If you're choosing to run your application on a fleet of auto-scaled virtual machines, well, you need people to manage those virtual machines, a skill set which is becoming less and less common nowadays. So you need to factor this in as well. So what does this actually look like when you're choosing where to run your application? Well, at the far right of that spectrum, you've got the services you probably thought about when I first said the word serverless. Things like Lambda, Azure Functions, Cloudflare Workers, Google Cloud Run. These services that promise this ideal world where you package your application code, push it, and don't care about the rest. AWS does everything else, right? But once you start to think about this as a bit more as a spectrum, you start to get some really interesting services. Services like Azure Container Apps, Amazon ECS. Is anyone using either of them two services, out of curiosity? Couple of hands. You're all Kubernetes people. Cool. These services where you can take a container image, push that to the cloud, say I want this much CPU, this much memory, and that's kind of it. The cloud provider is going to orchestrate that container for you. You're going to define some scaling behaviors, but mostly the only thing you need to think about is the stuff inside your container. The cloud provider cares about the rest. Then, of course, you've got your managed Kubernetes services, where the cloud provider takes on the responsibility for the control plane. You need to care about everything else related to Kubernetes. And then finally, right off the far end, you've got your virtual machines. And then somewhere else at the other side of Berlin, you've got that physical server under your desk that's still running applications. That way, not that way. The point is here not to try and convince you all that you should drop Kubernetes immediately and go and deploy everything to Lambda. The point here is to think about where the right place is to sit on this spectrum for the workload you're trying to deploy. The idea of thinking serverless first, being as far right as possible. And the word as possible is doing a lot of heavy lifting there. Because maybe you've got a use case where actually you're doing some data processing or you've got some ML inference going on. You need to be able to dynamically scale really specific types of infrastructure up and down. Well, in that case, of course, you're going to need that infrastructure flexibility. You're going to need to sit further to the other end of the spectrum. But for the vast majority of business workloads, sitting as far right on this spectrum as possible is going to be beneficial to not only you, but your users as well, because you can focus on delivering value for them. So Jane likes the sound of all of this. She thinks, I want to run my application without thinking about all that underlying stuff. I just want to build it, I want to deploy it, I want the cloud provider to think about the rest. So she goes off and she builds what is a typical serverless API. Some kind of API gateway, a separate serverless function for each of the individual routes on that API, and then some kind of persistence underneath. She goes off and she celebrates and she thinks, this is amazing, I'm going to get a promotion, I've just shipped this new service and I've added no additional overhead to the organization. Fantastic, brilliant. I know what some of you are thinking though. James has just been making a point about evolvability and the importance of evolving things over time. If you choose to adopt serverless functions, you're locked into that cloud provider forever, right? You've got vendor lock-in now, which means you can't evolve your system over time if things change. If you use serverless services, you're tied into that cloud provider forever, right? And I want to challenge that assumption just a little bit. First off, how you actually structure your applications is incredibly impactful. Using patterns like ports and adapters or hexagonal architecture or separating the code that does the infrastructure work from the code that actually solves the business problem allows you to build more flexible applications. And following the principles of things like the 12-factor apps, prioritizing stateless applications, externalizing your configuration, and putting these things together gives you a fantastic platform for evolving your systems over time. If the stuff that deals with infrastructure concerns is separate from your web frameworks, your database layers, your messaging technologies, it makes that application itself more simple to evolve. And even if you're not building user-facing applications, if you're on a platform engineering team, you can apply this same thinking. Separate the code that solves the business problem, i.e. allows a user to deploy an application to the platform, from the code that actually implements that under the hood. If that's running on top of Kubernetes, great. The user using that platform shouldn't know about Kubernetes, in my opinion. The other interesting thing about vendor lock-in is it's almost never your application code that is going to lock you in to a given technology. Almost never. It's data, state, is what's going to lock you in. So before I worked at Datadog, I worked for AWS for quite a few years, and I was consulting with a big energy company, big European energy company. And we were helping them migrate a lot of workloads from Azure to AWS. And they were super excited about this migration because they'd chosen to use Kubernetes. I'm not bashing Kubernetes, by the way. It does have very good use cases, I'm sure. But they were really excited because they'd used Kubernetes, which was going to make it really easy to take these applications from Azure and just drop them onto AWS. Simple. When we started investigating some of their workloads, a not insignificant portion of them was using Cosmos DB on Azure. Now, I don't know how familiar you all are with Azure or AWS, but you can't run Cosmos DB on AWS because it's a proprietary database technology. So yes, they'd chosen something that they would think they were portable from an application perspective. All of a sudden, they had a whole bunch of other problems to deal with. So it's your data that is going to lock you in. And of course, every decision you choose to make in your technology stack is a form of lock-in. So optimizing for strategies that allow you to evolve over time. If you're an application developer, thinking about how you structure your code and how you can port that around. If you're building a platform, think about how you could evolve that platform over time without affecting the users underneath. Now, a prerequisite to being able to evolve your system is, of course, understanding that system. If you need to be able to evolve it, or you're interested in which services are talking to which other services, you need to be able to understand what it is that system is doing. And when we lived in a simpler world where we had single process applications on single servers with a nice, simple Postgres database, this was a little bit easier. But now you're building these large, complicated distributed systems where you've got multiple business functions spread across multiple different cloud subscriptions. You've got different programming languages, you've got messages, HTTP, serverless functions, containers, and 12 different database technologies because microservices, yeah. What you need in modern software is the ability to ask questions of your system. Questions that you didn't know you needed to ask from a position that is external to your system. Understanding your system isn't dashboards. Understanding isn't metrics. Understanding isn't logs. Understanding is being able to ask questions you didn't know you needed to ask when you built the system. Which is a strange way of putting it, right? How can I ask a question I didn't know I needed to ask? Well, let's consider this really simplistic architecture diagram about what plant-based pizza looks like. And imagine one day there's an outage. The order processing service goes offline because the database runs out of disk space, for argument's sake. So you get paged, you wake up, you realize the disk space has run out. Thankfully, you're using some managed cloud database, so you can just push some more disk space in there. Database comes back online, service recovers. Hopefully at this point, you're going to do some kind of post-mortem. You're going to look back at what caused the issue. You're going to realize that it was disk space on the server that caused the issue. You're going to put some kind of monitor or metric in place. You're going to have some kind of alert. And then hopefully this never happens again. You get an alert and you can go and fix that issue proactively. Now, because you've put that metric and that alert in place, the chances of your system failing in the same way again are almost zero now. That's not to say you shouldn't do this, but there's a finite set of things you can predict ahead of time. The vast majority of failures you're dealing with in distributed systems are unknown unknowns. These systems fail in new and novel and interesting ways all the time. They're being updated frequently by different teams of people, different release cycles, different SLAs, different business pressures. Heck, even some of these teams aren't even looking at the code they're shipping anymore. They're just letting it go out to production. How could you even begin to predict all the different failure modes that your system could get into? It's physically impossible. And if you think you could, I'm sorry to break it to you, but you can't. So for that reason, when it comes to understanding modern software, the most important thing you can do, whether you're a platform engineer or a developer, is look at distributed tracing. Distributed tracing is what allows you to understand modern software. And just to level set on some terminology, the top level here is a trace. A trace is an end-to-end flow of a request. A trace is made up of lots and lots of individual spans, and those spans can span multiple different back-end systems. Now, to caveat what I've just said, that distributed tracing is the most important thing you can do, that's distributed tracing with lots and lots of context. You can add tags and attributes to this data to allow you to start to ask these questions. You want this ability to ask questions of your system. So it's actually context that's the most important part of understanding modern software. And I think it's interesting to think about context in two different buckets of things, if you will. The first bucket of context is technical context. Context that's familiar to every single one of us in the same room. We all care about the same stuff here. The HTTP route, the HTTP status code, the SQS queue that you're sending the message to, what cloud provider you're using, what availability zone, what region, what account. All of these things are context that you can add to your understanding of the system to allow you to ask questions. And OpenTelemetry actually publish a set of semantic conventions or best practices for a whole range of different things. There's semantic conventions for HTTP, for messaging, for Gen AI, for functions, for cloud, for compute. This defines a standardized set of attributes that all of your telemetry should have. So the messaging semantic conventions include things like the operation name, the system that you're sending the message to. So this is a order confirmed queue, and this is a SQS queue, happens to be. Now, this is really interesting when it comes to understanding, because you can start to ask really interesting questions like, how many 500 status codes have I had in the last hour? Or how many messages have been sent to the order confirmed queue? Now, where this gets really powerful, though, is this ability now to be able to zoom in and zoom out. You can ask the macro level question of how many 500 status codes have I had in the last hour? Okay, there's been 10. Let's zoom in now to those specific requests and actually see how those specific requests flowed through the system and what caused that 500 status code to happen. So that's one side of context that's useful to all of you and it's familiar to whatever kind of system that you are building. But the other type of context, and the more important in my opinion, is business context. Context that's unique to your specific business domain. The order ID, the account ID, the user ID, the action they're trying to take, all these things that are very unique to your business domain. Things that allow you to ask questions of your system. And historically, maybe you've got an outage, something's happened, a given user is having a problem. Historically, you'd go off to your observability backend and you'd look at, show me all the telemetry for user James test. And you can have a look at how this user is interacting with this system. How is this user, what components is this request touching? How are things related to each other? But LLMs are starting to make this even more powerful. And I am a massive skeptic of LLMs and AI-assisted coding. But this is one specific situation where I actually think there's some potential use cases here. And that's not just because I work at Datadog, I promise. I would be saying this if I didn't. Because here you've got lots and lots of data, huge amounts of data, that you want to be able to ask questions of using natural language. It's kind of what you really want to do to understand your system. Well, that seems like a pretty useful use case, because now you can start to ask interesting questions. What's the P50, P90, and P99 latency of this API in the last day? Can go off, summarize all the telemetry that you've got, give you overall latency, and not that I asked for it, I'm getting a per endpoint breakdown of the latency as well. I can ask questions of the system to understand how the system is working. And you can even bring this functionality wherever you're using your LLMs. This is the Pi coding system. If you're not familiar with Pi, it's kind of like Claude Code, but more open source and a bit more open and extensible. You can ask these same questions there. What has the user, James Tess, been up to recently? It's going to go off. It's going to find that, well, this user's been interacting with these endpoints on the API. There's been quite a lot of requests. There's also been these failures that have happened. Some problems have happened. Some things have gone wrong for this user. And actually, because I'm now in a coding assistant where I'm next to my application code, I can extend this question even further and say, well, I've seen these 500 errors. Let's actually now ask the question, go and have a look at the application code, correlate that with the telemetry that you've got, and work out what exactly is causing the problem. Great. It seems like there's some kind of error when an application gets closed down. The point I'm trying to make here is that understanding your system, having this context available, helps you understand the complexity of your system, helps you understand the different components. And when it comes to actually doing this in the real world, in 2026, there's no better way than using OpenTelemetry. If you're instrumenting applications, you're instrumenting application code, you should be using OpenTelemetry. Standardized set of APIs. Doesn't matter then if your app's running on a container, in a serverless function, and a server under a desk, you can ship that application to wherever you want. So this is great for Jane. She's optimized for evolvability, optimized for dealing with the complexity that the modern world of developing software imposes upon her. And importantly, she's also got the ability to understand the system once it's running in production. This can help her make more strategic decisions about how exactly she evolves this system over time. And this is great for Jane, of course, but what does this mean for all of you when you go back to work tomorrow or next week or whenever it is you're next in the office? The first and most important thing is to focus on the right complexity. Focus on the things that your users actually care about. Whether you're a platform engineer, whether you're building user-facing software, whatever it is, focus on the complexity that your users care about. And all that complicated other stuff, try and minimize that as much as possible. Secondly, design for flexibility. Design for the ability to evolve your system over time. Make this a first-class citizen. Think about how you can change things. And finally, choose the right tool for the job. Think about that spectrum of options. Sticking religiously to one technology that maybe your company imposes upon you, maybe that you like, is great in a lot of cases, but I'm sure in most of the workloads that all of you are building, there will be use cases for other technologies as well. Understand that certain workloads might better suit functions, and maybe they do. And actually at Datadog, every year we publish what we call the State of Reports, where we look at all Datadog customers' data, we draw a bunch of insights, anonymously of course, and we look at what we can see about what's happening in the industry. And late last year we published the State of Containers and Serverless Report, which is basically just a look at the modern application development and deployment ecosystem. And one of the most interesting facts I found, at least, was that 66% of customers who are using serverless functions are also using containers. 2/3 of the Datadog customer base are using both. So if you want to learn more about how Datadog can help you manage your complexity or manage the things, there's a booth just outside that door there. Go and chat to one of the guys there. They'll be able to help you out. Otherwise, if you want to hear more about these topics, you want to get a little bit deeper into the practicalities of how you can actually combine these two technologies together. I'm giving another talk at 4 o'clock today in a room down there. If you want to come and catch that, then I'd love to see you there. If I've bashed Kubernetes too much and you're all really mad at me, then that's cool as well. Enjoy the rest of the conference, and thank you all very much for listening.